Hi. Okay, cool. It's working. I'm Seth Samuel. I'm from New York, Portland, various other places. Portland, now most recently New York City. I can never move again because it would destroy the symmetry of where I live, and I just can't live with that. I'm here to talk to you about arbitrary computation on the GPU with WebGL, which is the most overworked talk title I think I've seen today, so I'm proud of that. But I haven't been able to come up with something better. It's heart WebGL because I was debugging some issues with my slides and UTF-8 and Unicode and all that, but I liked it so much because I do heart WebGL that I left it there. I'm Seth F. Samuel on Twitter and Seth Samuel on GitHub, where you can find these slides and all the code for all the demos. So that if you are interested in how it actually works, you can go see. All right, what's WebGL? So WebGL is a JavaScript API that lets us as web developers talk pretty directly to the graphics card, much more so than we do if we're using Canvas or DOM. And it's really powerful because of this. WebGL is basically the closest you'll get to the metal as a JavaScript developer in the browser. Maybe when ASM.js comes out, it'll be similar. But right now, by far, WebGL is the fastest way to run certain things. And that's awesome. So how does it work? Basically, we live in the JavaScript world. There's an API to WebGL where we send off function calls. WebGL packages those up, sends them off to the operating system. They go through the graphics driver to the GPU. The GPU then paints them onto a HTML canvas, which we as JavaScript can then interact with. There's some fun little security flaws here, because it turns out that your shader code, which we'll get to in a minute what that is, actually does run straight on the GPU. So a lot of people were concerned, because this is sort of breaking the JavaScript sandbox. So don't do evil with this. Do good, because it's really cool. All right, so I mentioned shaders. This is the basic WebGL pipeline. You put in data, you have that data pass through what's called a vertex shader. The vertex shader passes stuff off to the fragment shader, and then you get graphics. If you're going to do WebGL, you're going to get used to really awful nomenclature. Why are these things called shaders? We'll hear about some even worse named shaders later. So the vertex shader takes data and transforms that data, usually something like an array of things that look vaguely like coordinates, into actual 3D space coordinates. The fragment shader then places color into the fragments that are outlined by those coordinates. Or if you're working in points, then just those individual points. And then all of that gets flattened down into a rasterized image and drawn onto your canvas. All right, so simple example. This is just a simple gradient. Hopefully everyone can read that. It's a little small. Laser pointer. Yay. OK, cool. So this is GLSL shader language, which is kind of funky. It's a lot funky. It's very C-like, including the fact that we don't actually return things. We actually set variables for our return value. Because, so this little GL frag color thing over here, when you set a value for that in your fragment shader, that is the color of the pixel at this point. And you pass in what's called a vec4, which is a fancy name for an RGBA value. This vchord here is something that the the vertex shader is handing off to us. It's just our place in space. Like you can think of it as 2D space and a S and T are what we call X and Y when we're talking about fragment shaders, because nomenclature. You can, in fact, use X and Y there if you want, but just typically use S and T. We're just going to make blue 0 and alpha 1, because sure. All right, and we get this. So this is actually WebGL drawn in an iframe right now. This is live. So you can see we've done a little magic behind the scenes for those of you who know about WebGL to make our coordinate space friendlier to JavaScript. So this is 0, 0 up here. This is 1, 0, so that's S equals 1, so that's all red. There's no Y, or T, so there's no green, so it's all red. Here it's all green, and here it's yellow. You're going to have to take my word, that's yellow over there. Cool, so we got a gradient. So what's cool here is that this is all happening in parallel. So every single pixel on that gradient is being calculated and drawn at once. It's not sort of stepping through, it's doing it all at once. For a gradient, that's not that impressive. It's really easy to draw a gradient, probably. But we're going to get to something where it's a lot cooler. All right, edge finder, a little more complicated. Those who don't know what an edge finder is, let's say we have an image, we want to find edges in them. The simplest way to do this is you basically step through every pixel, you look at the pixels next to it, you have some threshold for how different they have to be an edge. So if one is white and the other's black, that's definitely an edge. If one is red and the other's kind of a purplish edge, maybe it's an edge, maybe it's not. So basically, we've got this little texture guy up here, so that's the image we pass in. And then this little jig number here, we step a little bit over. We have a threshold where we say if it's more different than that, what color did I pick here? Purple. Then make it bright purple, otherwise make it black. All right, so here we have a small child attempting to eat an entire block of cheese, which, we've all been there. So let's see if we can find the edges in this image. Cool. So this little slider over here is our threshold parameter. So if we bring this all the way up, then you can see we're being really strict about edges. So we're saying two colors have to be really different to qualify as an edge and get drawn as purple. If we bring this guy all the way down, then basically everything counts in as an edge. In practice, if you were actually using an edge finder, you'd go here. So what's really great, oops, gotta get out of the iframe. If I turn on my FPS meter, a little peek behind the curtains, JS lint with no console log on would just sit in the corner and weep at my demo code, as you can see by the sheer number of console logs up there. But if we turn on the frame rate, it's 60 frames per second. We're going through here. We're not doing anything at all. And yeah, that FPS is not budging. And the reason is, just like our gradient, every one of those pixel calculations is happening in parallel on the GPU. Go ahead, console log. All right, and particles. It's not a WebGL talk without a particles demo. So here, much like we had GL frag color before, we have GL position, which is in the vertex shader. And we do a bunch of sine and cosine math, basically to spin things around in circles in 3D space. And what we get, oh, come on, it's a particle demo. You can do better than that. Yay, there we go. OK, cool. That is the best reaction of any slide in this talk, always, because it's got particles. So that's like 50,000 particles on my crappy little MacBook Air, and it's 60 frames per second and spinning and awesome. So why is WebGL so powerful? And it comes down to you have two main engines on your computer. You have a CPU and you have a GPU. CPU is a general purpose processing unit. It does lots of things pretty well. Your GPU is specialized. It does a much smaller subset of things very well. And what it does is relatively small set of math, all in parallel, all really fast. So for things, anything that we can describe in that way, it will be way faster than the CPU. All right, so someone came along and was like, wait a second. There's other kinds of math we want to do all in parallel that we can describe in this same way. And we'd like to do it without all the overhead of pretending we're doing graphics, right? And so just like WebGL is a front on top of OpenGL, there's also this thing called OpenCL, which is, I think, Open Computing Library. Yeah, I'm going to say that's true, and no one correct me on Twitter. And so this is awesome. So OpenCL, if you're writing system software, lets you run anything you'd like to on the GPU without having to pretend you're running graphics. So OpenGL WebGL, OpenCL, WebCL, and it's coming soon. It's not coming. It's been coming soon for years. It's stuck in committee hell, and we're not waiting for it anymore. We also have compute shaders. I told you there'd be something even more ridiculous than vertex shader and fragment shader. Now there's compute shaders. What computing has to do with shaders is we call things in OpenGL and WebGL shaders, and so they tacked compute onto the beginning. And so we're stuck with compute shaders. They're also coming soon. They may be coming sooner, but still not very soon. So yeah, let's just do it ourselves. We're developers. We just like building things. So we can get data in. That's pretty easy. We have lots of ways of getting data in. We can do math because we've got shaders. How do we actually get the data out of the WebGL? If you remember the slide all the way back, there was just a one-way arrow to the OS and the GPU, and then it eventually comes back to the canvas as just pixels. Well, pixels are the answer. That's all we got. Luckily, the arrows between the JavaScript and the HTML canvas are two-way, because we have canvas.getImageData. This lets you dump all of the pixels, or a subset of them if you only want a subset, from an HTML canvas back into your JavaScript as a nice little array of, forget what it is. It's like 8-bit ints or something like that. It's great. All right. There are some challenges. The big one is this. So there's a lot of like nitty-gritty stuff of coordinate spaces, because it turns out WebGL 0, 0 is in the bottom left, but if you're talking about Canvas and other JavaScript imagey things, 0, 0 is in the top left. That gets really annoying, but you throw a few like negative signs in there, you're fine. Lots of little boilerplate with WebGL. It's fine. We got that solved. This one we can't actually solve. It turns out that getting data into WebGL, it's a little bit expensive. Getting it out of a canvas is really expensive. It's roughly linear with the number of pixels with a pretty nastily high coefficient. So you're not really able to do this for things where you just want to do like 2 math operations. It's just not worth it. So we're going to be looking at applications where we're going to do a lot of math inside of there, so it's worth this overhead. All right, so we're going to do matrix multiplication. We'll have a quick review of matrix multiplication in a second for those like me who had to go look up in your algebra textbooks and also go to Wolfram Alpha to make sure that your algorithm was right and doing the math right. It does, I promise. So this is pseudo GLSL because there's a whole lot of casting and awfulness that you have to do to actually do this. The actual code is in the slide source. The basic idea is for every single pixel, we're going to loop through all of the other pixels, which we're going to represent as 2 textures. We'll get to why we use images to pass the data in later. Do a bunch of math, sum it up, and output. So this is matrix multiplication. So the basics of matrix multiplication is you got 2 matrices of we're just working with square matrices. You take the left one, you turn it on its side, you like pass it through, and you do math. It's okay. So the top left one here is going to be the sum of the products of the top row of the left one and the first column of the right one. So that's going to be 0 times 8 plus 9 times 3 plus 8 times 7. And I'm not going to do that math because I drew a really hard one. But it's that. So there we go. So we've got a 3 by 3 matrix. We've done multiplication, and we've got an output using just plain old JavaScript. Now we're going to do it on the GPU. All right, so they match. That's good. You really want that in your demo, that like the 2 pieces of code actually do the same thing. But as you can see, it's actually way slower on the graphics card using WebGL. It's really, really badly slower, and that's because of that serialization cost that I was talking about before. So we're just going to beef up the size of this thing a little bit. Powers of 2 are always fun. All right, look. So the GPU's basically not gone up at all. The CPU's gone up a ton, and we're already actually outpacing it a little bit. We're a little bit into the noise range here, so we're just going to keep going up. All right, so yeah, that's a lot better. All right, let's just go all the way up. I got plenty of time. All right, and so this is the part of my talk where I vamp for about 3 minutes, because we're going to have to sit here for a little while. The little JavaScript, your script has become unresponsive. Pop-up's going to come up. If I don't see it, yell at me, and I'll hit the keep going button. So yeah, a few talks, things that came up building this talk. That little spinner there is just a single div with some styling applied to it. It's a pretty standard technique, right? So it's got a not active state where it's just hidden, and it's got a active state where it has a animation rotating it and some size. Oh, there you go. Wait. So this is using CSS transforms, which are GPU accelerated, which is great. So even though I'm not going to open the console, because if I like screw this up, we're going to have to wait another 3 minutes. But trust me, we are like throttling the CPU right now as this tries to do all that math. So 1024 matrix means that there's a million elements that it's going through, and everyone doing its own million operations. So it's a lot. So that spinner is actually still able to spin now because it's all being done on the graphics card. But it turns out that there's a little bit of overhead before that actually gets pushed off onto the graphics card to keep going. We actually just heard about web workers, which was really cool and well-timed. So that can keep spinning because it's all on the graphics card and none of it's touching the CPU. But adding a class, which is how this thing becomes active, triggering the repaint, which realizes, oh, I should send off this div to the graphics card to be spun, does take CPU. So there actually has to be a little bit of a timeout before starting this calculation so that the browser has time to get that thing spinning so that we can see the nice little spinner that tells us things are going. Fun little UX tip, even if if your like pause is somewhere in the like few hundred milliseconds range, that's long enough. You want to let the user know that you're doing something. But it's actually not very long as far as users recognizing a spinner. And it can actually be nice to show a spinner for a little bit longer than the calculation actually takes. So those earlier examples when we were running with like 3 and 10, whatever, only took like 10, 20 milliseconds, but the spinner actually shows for about 500 milliseconds, and that both gives, we both make sure that that spinner is going and like happy and spinning before we start hammering on the CPU, and gives the user a nicer feel about that. And I forgot to set my timer, so I don't know how much longer we have to go. That's all right, we'll tell more stories. Another cool tip from all of this. Oh, one cool tip. The CPU is still doing stuff even while that dialog is up. So it doesn't actually matter how fast my response time is there, because it will eventually finish, even if I don't hit wait. So a few things about GPU at WebGL shaders. In the bad old days before ES 2015, the way you did DSL shaders was terrible. Basically, DSL shaders are little snippets of programs like we saw before. In fact, they're quite a bit long, not quite a bit, but they're a bit longer than that with a lot of boilerplate. And so the way you used to do it, because there weren't multi-line strings in JavaScript, was you'd have like a script tag in your DOM of type text whatever. And then you would read out of that and then pipe that into WebGL. It's terrible, ugly hack. And if you had variables inside of your shaders, so WebGL shaders can't do dynamic loops. So you can't say for I equals 0, I less than array.length, I++ in JLSL. Instead, you have to hard code that value at shader compile time. It turns out ES 2015 string has solved both of these for us, because we get multi-line strings and you get variable interpolation. Woo! Yay! And so the quick little lesson is that when you load a shader multiple times, which you do in this application and in some others, you will actually find out that unless you tell WebGL, no, really, like, clobber the old one, put this new one in there, it will silently just run the old one. So as that slider up there changes, where all it's doing originally was reloading the shader, and it wasn't working until I said, oh, when we change that, like clobber the old WebGL, give us a new one. There's probably a more elegant way to do that, but for this purpose, it was just like, no, give me a whole new context. All right, cool. So that's really long. This is at the point where we're benchmarking things in milliseconds, and it's a lot. It's about it's a little slower when I'm presenting. Normally it's around 200. 230,000 milliseconds, so like 3.5 minutes. That's bad. All right, let's go to GPU. That's faster. Ooh, good, and it worked. So one last little behind the scenes bit. This demo does not work on my phone. Past a certain size, I think it's because the precision of the math on a mobile GPU is actually lower than it is on a nice proper desktop CPU. So I was testing on my phone because these slides are fully like phone responsive and all that. I was like, oh, this is cool. Let me run the demo. It works. Let me see how long it takes to do a 1024 by 1024 matrix on my like iPhone SE. And the answer is a while, and then on the GPU, it's still pretty fast, but it's wrong. The numbers are all like a little off because we're doing a lot of math, and those small precision errors add up a lot over 1 million elements. So yeah, that's awesome. That's way faster. That's actually like worth the overhead faster. All right, so why? Well, like we talked about, the GPU does things in parallel, and it turns out that ON cubed is bigger than ON. Big O notation gets like kind of a bad rap because it gets asked in like job interviews in inappropriate times, but sometimes it actually matters. This is one of those times where it actually matters. The edge finder algorithm earlier, if you do it in the CPU, is n squared. If you do it on the GPU, it's also n. N here is the width of the square. It's just convenient to do it that way. You could do it as the total number of elements, but then you get all these over 2 things in your exponents. And it's just easier to think of this way. So here's a little graph. Hopefully those colors can come through. So the big one, that's n cubed. The one in the middle is n squared. And that flat one is n. So this is from n from 0 to 5. So even at 5, we're seeing a bit of distance here. From 0 to 10. So at like 100, we've totally lost n, and n squared is looking pretty flat. And at a 1024, which is what we just did, there's nothing. N cubed is terrible. That's why it took 230 seconds, because n cubed gets really big really fast. And so going from that to n is a pretty big improvement. All right, so we've got like a cool proof of concept. We've got like a nice example of how we can actually do a lot of math really fast. What can we use this for? All right, hash collision. If you want to like do a lot of hashes all at once, if you're a white hat hacker, it's to make sure your password system's safe. If you're a black hat hacker, it's because you're trying to find out other people's password systems aren't safe. Bitcoin mining, basically all Bitcoin mining is done on the GPU because it turns out doing lots and lots of hashes at the same time is much better on the GPU. This is actually where this talk came from. I was trying to come up with a way to have an application that people sort of paid for in micropayments by doing Bitcoin calculations for the provider. And it was like, oh, well, they're going to want to run in their browser. And oh, how do they do that? Well, maybe WebGL, we can actually run the Bitcoin mining. Spoiler alert, you can't. We'll get there. Media encoding. You can, if you wanted to do like video or image encoding, that's a lot of things. There's a lot of parallel block operations that you can get out of there. Machine learning is basically just a lot of math. It's basically a lot of multiplication and addition, all in parallel. Signal analysis. This one's kind of cheating because audio is basically just video. Like they're all just sort of signals, but it's also big potential application. Protein folding. You notice these last two sound a lot like things that you can get screensavers for because they are highly distributable, highly parallelizable, and use the graphics card. All right, actual applications. What can we actually use this for? Can't use it for hash collision. Can't use it for Bitcoin mining. Can't use it for media coding. Maybe machine learning. That one actually I haven't gone to work yet, but hopeful. Signal processing, maybe. Protein folding, maybe. All right, so what are our actual blockers to these cooler applications? Again, much like trying to eat an entire block of cheese, this has happened to all of us at one time or another. That's not my cat, but my cat would totally do that. Here's the big one. There are no bit operations in the current implementation of WebGL. Sad face. So WebGL has been around for a few years. It uses a very out-of-date version of the shader language, which has no bit operations, no XORs, no bit shifts, none of that fun stuff. We've spent the last, very smart people, other than myself, have spent the last several decades making really awesome algorithms that take advantage of the power of bit operations because we're running everything on computers and they're really good at doing stuff with bits. So why don't we build algorithms that do stuff with bits? So basically, any powerful modern algorithm you're going to run into, whether it's hash, most of them rely on hashes, and even if they don't rely on hashes, a lot of times they're doing stuff a lot like hashes do, involving bits moving here and there, and you can't do them in WebGL right now. So no. Unresponsive window, we just heard all about making your web sites really smooth and never going over that 16 millisecond limit. It turns out that WebGL runs on the main thread. It runs on the GPU, but it turns out you still need the GPU to draw your web page. So if you're locking that up, you're basically not going to be able to do anything. And OS low timeouts, this is another fun little gotcha. It turns out different operating systems will at some point decide your shader's been running too long. There's not really any warning or error, it's just gonna return something. Might be a black pixel, might be if you had already written a value to GLFrag color, some other color. But yeah, they basically say if an individual shader has sort of run too long, where too long is usually 2 or 3 seconds, it'll just kill it to stop you from murdering the whole OS. All right, how can we solve these? Because we want to make these work. Newer shader version has bit operations. This would be amazing if browsers upgraded to, this isn't even the latest. This is like still 2 or 3 versions old. If browsers upgraded to this, we could do all of that cool bit operation stuff in the browser, in WebGL, super fast. Canvas WebGL in the web worker. This is something that's in progress, and unlike Compute Shaders and WebCL, is probably actually coming soon. This one seems like browsers are actually working on it, and we'll hopefully get it soon. So a lot of this image work and web work can get pushed off into those workers. All right, sum up. I've got 59 seconds. Cool. WebGL is awesome. You can do some crazy stuff with it if you're willing to sort of shape your algorithms in a friendly way. And you get it out, and you can do stuff way faster than the CPU for a very limited set of operations, which will hopefully get slightly less limited in the future. Thanks.